Hello everyone. So today we're going to continue on Laplace Transform. So if I remember correctly, the last video we get to talk about how to do inverse Laplace Transform, which is basically to kind of use this table right here to try to figure out what the function would be if we know what the transform is. So I would suggest that while you're watching this video, go on to Google Classroom and open up the document for the table for Laplace transform, because that's what we're going to be using. So what I want to do today is just go through a few more examples on using the formula, using the table to kind of generate, oops, the function y if you do know the Laplace transform of it. So remember, the general idea of solving using Laplace transform to solve a differential equation excuse me, with initial condition is to first start by doing the Laplace transform of the entire equation and then do a partial fraction on the Laplace transform of the unknown function y. And once you did that, then you're basically using the table of Laplace transform, and since you know the Laplace transform of y is, you can then reverse engineer what y is. So we are now on the last step of the problem, which means that we have the Laplace transform of y, we have it kind of broken down into partial fractions. Now it's just a matter of using the table to find out what y is. So here's our next example, which once again just came from one of the examples that we've done. Suppose, let's say we're given the Laplace transform of y is equal to this 4 over x minus 1 plus 16 over x minus 2 squared. Then the question is asked you to go and find y. So obviously the answer for y is this. Y is basically the Laplace inverse of 4 over x minus 1. Let's take an extra step. Plus 16 over x minus 2 squared. Okay, so now the question is, what would be this inverse going to be? So first of all, remember, because of the linearity of Laplace transform, I'm going to pull out the 4 and focus on 1 over x minus 1. And pull out the 16 and focus on the Laplace transform of x minus 2 squared. Oops, there's no square here. All right. So now then what you're going to do is basically now look at the Laplace transform and try to find the appropriate formula that would allow you to actually do the Laplace transform. So it's just a matter of looking at the formula and trying to pick out the one that will work. So clearly this one right here, oops, this one right here is basically rule, and I'm going to reference them to the table. So this one clearly rule number 3, which say that Laplace transform of e to the at is 1 over, I should say s, actually, s minus a. And actually I should change it to s for now. Oops. Let me do that right now. There you go, much better. So that's our basic rule. So in this case, our 1 over s minus 1 technically is 1 over s. Actually, I don't have to do anything because it's already 1 minus. So therefore, we just have the 4 in front. That's all that is. So now the question is, what happened to this one right here? So this one using a different rule. So if I'm looking at this correctly, that's rule number 4, which is Laplace transform of t to the n e to at is equal to n factorial s minus a to the n plus 1. So as I say, the first one here is simple, so I'm going to do that. So that just becomes 4 multiplied by 1 over, multiplied by e to the at, which in this case a is 1, so become e to the 1t. So now the question is, what do I do with the second one? So the way to do that is to identify two numbers from the formula number 4 that matches the equation. So in this case, I can see clearly that a would be 2 and n is 1. So therefore, I do need an n factorial on top, which is 1 factorial, and technically that's 1, and which we do have a 1 on top. So we actually don't have to do anything, but just simply recognize that, well, that would just be 16 t to the first, because n is 1, so I'm going to just say t. E to the at, since a is 2, is 2t. And so that gives me my answers. So unlike the example that we've done before, where I have to kind of modify something on top, this one kind of does not, which is nice. Now let's try another one that may be more complicated. Okay, let me see. We can try, maybe we'll try this one, okay? Okay, maybe this one we do a little bit more work and see if we can figure this out. So let's say given L of y is equal to 3x to the third plus 7x minus 4 over x squared plus 2 squared. So I don't think we did this problem. Let me just take a quick look. I don't think we did this one. Nope. Oh yeah, we did right there. So we're going to just use the answer here. So let's say this is what we have. We're going to ask you to find y. So according to what we have done before, let me just take a quick look. It's right here. So this is the partial fractions. So I guess I'm actually probably, let me see that. No, I didn't fix that here. That's why. Okay, I'm going to fix that to s. And the reason why I'm going to fix that to s because that's the variable that we use in the table for us. So I'm going to use that. I have to remember to do that. So let's say this is this. So try to find y. So first of all, that would mean that y would equal to the Laplace transform of this fraction, 3s to the third plus 7s minus 4 over s squared plus 2 squared. And according to our previous example, let me see, right here, so we can actually just write this out. So let's see. Okay, I think I got it. Let's hope I don't make a mistake. So that would be 3s over s squared plus 2 plus s minus 4 over s squared plus 2 squared, I think. Let me just double check to make sure. Okay, yes, I think I got it. Okay. So therefore, just become the Laplace transform, Laplace inverse of these two fractions. So once again, what we're going to do is the following. So here, this is a little tricky because you have to kind of identify the proper Laplace transform to use. So if I look at all the rules right here, so I'm looking at the list, I notice that this one right here, or maybe I would do this first, that would equal to the Laplace transform inverse of 3s over s squared plus 2 plus Laplace inverse transform of s minus 4 over s squared plus 2 squared. So now it's just a matter of identifying the correct rule to use. So I'm looking at the list, and it seemed to me that number 5, oh no, actually not number 5, number 6 is probably the rule that we want to use for the first one. So this one right here seemed to me is number 6. So what's the difference between number 5 and number 6? Number 6 has an s, that's the key. So number 6, the rule states this: Laplace transform of cosine bt is equal to s over s squared plus b squared. So clearly what I'm going to do first thing is I'm going to take out the 3. So now I do have s on top, I do have s squared on the bottom, and I do have a 2 in place of what b squared is. So therefore, seem to suggest that b squared is equal to 2, imply that b must be equal to radical 2. So therefore, I can say that this front part must be equal to 3 cosine radical 2t. Okay, so now let's do the end of this. So what happened to this thing right here? So let's see if there's one that fit this one right here. It look like 8, but 8 doesn't work because we need s squared on top, and we don't have that. And so I don't see anyone specifically work for us. Let me see. So look like these are the two that would work. So here's this one is a little tricky. So let's see if we can do this. I'm going to go and separate this into two. So I'm going to go and clean this out right here. And I'm going to go ahead and break it down into these two things. I'm going to say Laplace transform inverse of s over s squared plus 2 squared plus minus 4 Laplace transform inverse of 1 over s squared plus 2 squared. And now I can find a proper rules for this. Okay, seem to me that this one right here follow rule number 7, which said that when you take Laplace transform of t sine bt, you get 2bs over s squared plus b squared squared. So you might be thinking, like, how do I know? Well, here are the two things I'm looking for. I do need s squared plus something squared. Okay, so that automatically, if you look at the rules, it looked like 7, 8, 9, 10, 11, 12. All of those seem to be feasible. But then I also need the top to have an s in this case. Okay, so the only one that top has an s is 7. 7 the only one have s. All of the other one have a s square or s cube and things like that. So we don't want any of those. Okay. And now then, what do we do with the second part of it? Well, second part means I have to look for the top that doesn't have any s. So that seems to me that the only one that has the s squared plus something square on the bottom but doesn't have an s on top is rule number 9. So seem to me that this one, I'm going to put on top so that room is rule number 9. We'll say Laplace transform of sine bt, I don't know, I have room, minus bt cosine bt is equal to 2b to the third over s squared plus b squared squared. Okay, hopefully you can see that. So that one would be that. So now just a matter of trying to fix it so that it works. So now once again, we're going to do the same thing. If I look at this right here, look at this, the first part right here, we can kind of tell that b squared must be 2. And therefore imply that b must be radical 2. Okay, so that's good. But there's a problem. The problem is that in order to use the formula correctly, I have to have 2bs on top. But we don't have that. We just have an s. So what I'm going to do is I'm going to make the 2b in front of it. So how do I do that? Simply by just multiply them. So therefore it will be 2 radical 2. The problem is if I do that, now my expression is out of whack. I have to balance it. To balance it, I'm going to do the exact same thing on the outside, but just upside down. And so therefore, those two things would cancel out. But I'll take those that on the bottom outside of the Laplace inverse, and then keep the one on top of the numerator, so that way you can fit theorem formula number 17. So I do that, that will be what happened, is that I would have plus t sine bt. So in this case will be t sine radical 2t. So take of that one. So now we can do the last part, which is this one right here. So how does this one work? Well, guess what? It works out exactly the same way. I'm going to go first identify what b is. So in this case, it seems to me that b squared is 2 again. So therefore imply that b is radical 2. So now what I need is that I have to have 2b to the third on the numerator, which I don't have. So I'm going to go and just put that in. So what is 2b to the third? That will be 2 radical 2 to the third. So if you think about it, that's 4 radical 2. So what I need to do is divide that by 4 radical 2, which just happened to 4 cancel out here anyway. Okay? So therefore, we have a radical 2 on the bottom. So now I can say that's plus 1 over radical 2. And then the inside will be sine radical 2t minus b, which is radical 2t cosine radical 2t. And now I can kind of clean this up. So let me see what I got. I have 3 cosine radical 2t plus t sine radical 2t. Okay, so both of them kind of work out. Oh wait, no, this one actually have a coefficient in front, which I totally forgot. Let's put that in. Is 1 over 2 radical 2 t sine radical 2t. So I'm going to have that 1 over 2 radical 2 t sine radical 2t. And then if I multiply the 1 over radical 2 into both of these, I'll have plus 1 over radical 2. Oops, 1 over radical 2 sine radical 2t minus the radical 2 actually cancel in this case. Just have t cosine radical 2t. And so that become our answers. I try to figure out how to plug into the formula. All right. Oh, actually, let me see. So I actually make a mistake right here. Let me just fix that right now. It should be minus right there because that's come from this minus right here in front of the 4. So therefore, it actually changes this to a minus and this to a plus. So I think now we're good. I almost forgot the to distribute the negative because it's minus the Laplace transform of 1 over s squared plus 2 squared. Now let's try another one. Let's see if we can do another one. And let's see how hard that is. Okay, now let's try this one. So this one is trickier to do. So let's see if we can figure this one out. Okay, so let's say we're given the Laplace transform of y is equal to negative 3s plus 1 over s squared plus 8s plus 21 find y. So now this one is definitely tougher to do. So therefore in this case we know that y must equal to the Laplace inverse of negative 3s plus 1 over s squared plus 8s plus 21. So the question is, how is that one going to look like? Which formula to use? So this one is tricky in the sense that whenever you see a trinomial on the bottom, it's kind of tell us that we have to use 15 or 16. Okay? Yes, that's how that worked. Okay? So, the way to get that to work is the following. Is to first try to figure out what happened to the bottom first. So the bottom is s squared plus 8s plus 21. What I need to do is kind of make it into the form that's like 15 or 16. Notice that formula 15 and 16 both have the same exact bottom, except the top, one involves just the number b, the other one involves s minus a. So one of them allow us to deal with the s, and the other one allow us to deal with the constant. And the problem is we have a constant and s together. So we're going to have to kind of figure out how to do that. So I'll show you how that's done. But first, let's deal with the bottom first. So how do I deal with this? So the way to do that is to do this, is to understand that what I need is to form a perfect square. So perfect square would be the following. To do that, you do a completing the square process. What I'm going to do is take the middle number, which is 8, and divide that by 2, which is 4, and then square. So that will be plus 16. And to make 21, I'm going to have to add 5 more. So therefore, now what I have is basically s squared plus 8s plus 16 plus 5, where 16 plus 5 give you 21. So I technically didn't change anything, but just simply break down the 21 into 16 plus 5. And now this front part right here can now be factored into this. And so from compare that to the bottom of number 15, I would now notice that I must have a equal to -4 and b must equal to 5. Oh, actually square root of 5, because it has to be b squared. That's right, have to be b squared, so square root of 5. So now I'm good, because now what I need is to try to figure out how to get the numerator to work. So what I need is the following. What I need would be a s minus a and a b. So that's tough. So how do it work? So now what I have is this, is -3s plus 1. And obviously it doesn't look like s minus a directly, but I could make it into somewhat look like s minus a. But I do need to deal with the -3. So what I'm going to do is this, I'm going to say, well, that would be -3. And let's just make it s minus a, which is s minus -3, s plus 4. Now, obviously, that is not the same thing as what's on top. Okay, so let's fix it. So how do I fix it? So if I look at this correctly, if I have to distribute the -3 to the 4, it will become -12. But I need +1. So what I'm going to do, how about if I add 13 to it? Then that would be the same thing. So notice that -3 times s plus 4 plus 13 would give me the same thing as -3s plus 1. Okay, so a little tricky to kind of think backward to try to get that to work. So therefore, meaning that this is actually equal to the same thing as Laplace transform inverse of -3s plus 4 plus 13 over s squared plus 4 squared plus 5. So now I'm getting somewhere. So what do I do next? Well, the next thing I'm going to do is I'm going to go and separate and now I'm in a much better position to use formula, because now this becomes formula number 16. So what's number 16 said? Number 16 said this. If I take e to at cosine bt, I get s minus a over s minus a square plus b square. So now if I compare the bottom to the bottom of what we have, I can now see that my a is -4, b is radical 5, and the top would have to be s plus 4, which I do have the s plus 4, except that I do have the -3, so I'm going to go and get rid of that and put it in the front. So therefore, that tells me the front part will be just -3 multiplied by e to the a, which is -4, t cosine bt, which is radical 5t plus. So now let's do the back end. The back end would be using, look to me like number 15. So rule number 15 says the following. Laplace transform of e to the at sine bt is equal to b over s minus a square plus b square. So once again, if I compare the denominator with the denominator I have, it seems to me that a must be -4 and b must be radical 5. So we don't have a radical 5 on top, but we can fix that. So how do I fix that? First thing, I'm going to move the 13 outside, and I'm going to put a radical 5 on top. But then I have to balance it with a radical 5 on the bottom. So now I'm ready to write it out. So therefore it becomes 13 over radical 5. And see, now this matches the formula 15 with a being negative 4, b equal radical 5. I can now plug it in and say, well, that's e to the negative 4t sine radical 5t. So some of these problems does require you to kind of do some work to try to fit into the solution. The key takeaway here is the following. If you do see a trinomial on the denominator, that almost automatically tells you it's 15 or 16. Okay? And then it's kind of tough to make it work, because then you have to first figure out how to put root 16 together first by doing this little thing on the side right here. And then once you do that, then you'll be able to properly separate into root 16 and 15. So keep that in mind, and something worth writing down for yourself. You see a trinomial on the denominator of the partial fractions, then automatically tell you that it has to be almost 99% has to be 15 or 16, root 16, 15 or 16. So I think I have time for one more problem, and that will probably be it. And I think that's could really be the last video for Laplace transform, because we've gone through every single step of the process, which there are 3 major steps, and each step requires a lot of algebra. The first step is using all the Laplace transform formula that we know to transform a differential equation into the Laplace transform, and then solve for the Laplace transform of y. The next, you are usually wind up having a big fractions on the other side. Then you can then use partial fraction to break it apart. And then the final step is then apply inverse Laplace transform, which require you to kind of turn each of the partial fractions somewhat into a way to fit into the formula. So I think we can do one more, and I don't think we have done this one, so I'm going to go and do this one. And this one would be easier than the last one, so hopefully, because I don't have much time to go through the whole thing. So let's do an easier one. Suppose Laplace transform y is equal to 7 over s to the 5 plus 6s plus 3 over s squared plus 25. You know what? Now that I think about this problem, it's not that good idea to have s and 5 and 2. And all of them together, but hopefully you get it. So s to the 5th on the bottom of the first fraction, 6s plus 3 on top, and the s squared on the bottom plus 25. Okay, so obviously this question asks you to find y, so let's go for it. So y clearly would equal to the Laplace inverse of 7 over s to the 5th plus 6s plus 3 over s squared plus 25. So what I'm going to do is break it down, and I'm going to just leave the variable, the coefficient inside for now until I know what I'm going to do with it. Okay. So now once again, it's just a matter of finding the right rule for that. So the first one is actually pretty easy. Because I have 7 over s to the 5th. So from what I'm looking at, that would be rule number 2. So this one is pretty easy. Oops. That will just be rule number 2, which states the following. If I take the Laplace transform of t to the n, that would equal to n factorial over s to the n plus 1. So if I'm looking at this correctly, seems to me that suggests n is 4. Because we have s to the 5th, so n must be 4, so that becomes 4 plus 1. So therefore, to use the formula correctly, I do need a 4 factorial on top, which I don't think that's 7, so I'm going to have to deal with that. So what I'm going to do first thing is I'm going to cross out the 7 and move the 7 outside. And then we'll do with n factorial, which in this case 4 factorial on top, and therefore I do have to divide by 4 factorial on the bottom to balance it out. And I'll figure out what 4 factorial is. I think it's 2 times 3 times 4, so 6 times 4 is 24, so I think it's 24. But we can work on that next step. So now come the tougher part is what happened to s squared plus 25, or 6s plus 3 over s squared plus 25. So if I look at just the bottom, s squared plus 25, that looked like s squared plus b squared. And then we have a 6s and a 3. So seem to me I'm using number 5 and number 6, and which is not surprising if you think about it, because 5 and 6 both come from a conjugate pair of complex root, just like 7 and 8 would, and just like 15 and 16 would, and just like 13 and 14. So a lot of these are actually come from conjugate pair. So therefore, it shouldn't be surprised that you're going to have to use like 2 rules for this. So what I'm going to do is I'm going to go and separate this first. So therefore, I'm going to separate into plus Laplace inverse of 6s over s squared plus 25 plus the Laplace inverse of 3 over s squared plus 25. And so now I can use the proper rule for that. So seem to me this one have s, so therefore this one will be using rule number 6, which said Laplace transform of cosine bt is equal to s over s squared plus b squared. So seem to me, if I'm looking at this correctly, I can see that b is 5, because b squared is 25, so therefore tell me b is 5. So that's pretty easy. And we don't need any number on top, just need the s on top. So I'm going to do is I'm going to go and cross out the 6 and put the 6 in front. And then that will do it. Okay. And now what happened to the last part? Let's see if I can do this. Oops. Whoa, okay, oh, right here, so that's good. Okay. So, and what happened to the last part? The last part right here, so this is rule number 6. So this is actually rule number 5, because we have a constant on top. Rule number 5. We'll say that Laplace transform of sine bt is equal to b over s squared plus b squared. So from what I'm seeing is b must be 5. So therefore I would need a 5 on top to use this formula, but we don't have that. We have a 3. So I'm going to do is I'm going to go and take the 3 out, and we'll put a 5 instead, but that would mean I have to balance it with a 5 on the bottom. So I think I have everything now. So now I fixed everything, and they now look like what the formula is. So I'm going now ready to answer the question. So therefore y would equal to 7 over 4 factorial, which is 24. And the Laplace transform of 4 factorial over s to the 5th fit in rule number 2 with n equal to 4. So therefore that becomes t to the 4th plus 6. And then now what's inside s over s squared plus 25, which now fit the Laplace transform for cosine bt, where b is 5. So I'm going to say this is cosine 5t plus 3 over 5. And now the last one now matches b over sine squared plus b, with b equal to 5. S squared plus b squared. So therefore that become now sine of 5t. Alright, unfortunately that's all the time I got, and I don't think that will probably be the last video for Laplace transform. So I know it's a little long, but hopefully that means you don't have to watch another video, so that might be worth it instead of me splitting into 2 videos. Alright, talk to you guys soon. Okay, bye bye.